For a topical guide to this subject, see Outline of the metric system. The International System of Units is the modern form of the metric system, and is the most widely used system of measurement. It comprises a coherent system of units of measurement built on 7 base units. It defines 22 named units, and includes many more unnamed coherent derived units. The system also establishes a set of 20 prefixes to the unit names and unit symbols that may be used when specifying multiples and fractions of the units. The system was published in 1960 as the result of an initiative that started in 1948. It is based on the meter-kilogram-second system of units rather than any variant of the centimeter-gram-second system. SI is intended to be an evolving system, so prefixes and units are created and unit definitions are modified through international agreement as the technology of measurement progresses and the precision of measurements improves. The 24th and 25th General Conferences on Weights and Measures in 2011 and 2014, for example, discussed a proposal to change the definition of the kilogram, linking it to an invariant of nature rather than to the mass of a material artifact, thereby ensuring long-term stability. The motivation for the development of the SI was the diversity of units that had sprung up within the CGS systems and the lack of coordination between the various disciplines that used them. The CGPM, which was established by the Meter Convention of 1875, brought together many international organizations to not only agree on the definitions and standards of the new system but also agree on the rules for writing and presenting measurements in a standardized manner around the world. The International System of Units has been adopted by most developed countries. However, the adoption has not been universal in all English-speaking countries. While metrication in the United States is consistent in science, medicine, government, and various fields of technology and engineering, common measurements are mostly performed in United States customer units, although these have officially been defined in terms of SI units. The United Kingdom has officially adopted a policy of partial metrication. Canada has adopted the SI for most governmental, medical and scientific purposes and for such varied uses as grocery weights, weather reports, traffic signs and gasoline sales, but imperial units are still legally permitted and remain in common use throughout many sectors of Canadian society, particularly in the building trade and the railway sector. History. The metric system was first implemented during the French Revolution with just the meter and kilogram as standards of length and mass respectively. In the 1830s, Carl Friedrich Gauss laid the foundations for a coherent system based on length, mass, and time. In the 1860s, a group working under the auspices of the British Association for the Advancement of Science formulated the requirement for a coherent system of units with base units and derived units. The inclusion of electrical units into the system was hampered by the customary use of more than one set of units, until 1900 when Giovanni Giorgi identified a need to define one single electrical quantity as a fourth base quantity alongside the original 3 base quantities. Meanwhile, in 1875, the Treaty of the Meter passed responsibility for verification of the kilogram and meter against agreed prototypes from French to international control. In 1921, the treaty was extended to include all physical quantities including electrical units originally defined in 1893. In 1948, an overhaul of the metric system was set in motion which resulted in the development of the practical system of units, which, on its publication in 1960, was given the name of the International System of Units. In 1954, the 10th General Conference on Weights and Measures identified electric current as the fourth base quantity in the practical system of units and added 2 more base quantities, temperature and luminous intensity, making 6 base quantities in all. The units associated with these quantities were the meter, kilogram, second, ampere, Kelvin and candela. In 1971, a seventh base quantity, amount of substance represented by the mole, was added to the definition of SI. Early development. The metric system was developed from 1791 onwards by a committee of the French Academy of Sciences, commissioned by the National Assembly and Louis XVI to create a unified and rational system of measures. The group, which included Antoine Lavoisier and the mathematicians Pierre-Simon Laplace and Adrien-Marie Legendre, used the same principles for relating length, volume, and mass that had been proposed by the English clergyman John Wilkins in 1668, and the concept of using the Earth's meridian as the basis of the definition of length, originally proposed in 1670 by the French abbot Mouton. On 30 March 1791, the Assembly adopted the committee's proposed principles for the new decimal system of measure, and authorized a survey between Dunkirk and Barcelona, to establish the length of the meridian. On the 11th of July 1792, the committee proposed the names meter, hour, liter and grave for the units of length, area, capacity, and mass, respectively. The committee also proposed that multiples and submultiples of these units were to be denoted by decimal-based prefixes such as centi for 100th, and kilo for 1,000. The law of 7 April 1795 defined the terms gram in kilogram, which replaced the former terms grave and grave. And on the 22nd of June 1799, the definitive standard meter des archives and kilogram des archives were deposited in the Archives Nationales. On 10 December 1799, the law by which the metric system was to be definitively adopted in France was passed. During the first half of the 19th century, there was little consistency in the choice of preferred multiples of the base units. Typically, the myriameter was in widespread use in both France and parts of Germany, while the kilogram rather than the myriagram was used for mass. In 1832, the German mathematician Carl Friedrich Gauss, assisted by Wilhelm Weber, implicitly defined the second as a base unit when he quoted the Earth's magnetic field in terms of millimeters, grams, and seconds. Prior to this, the strength of the Earth's magnetic field had only been described in relative terms. The technique used by Gauss was to equate the torque induced on a suspended magnet of known mass by the Earth's magnetic field with the torque induced on an equivalent system under gravity. The resultant calculations enabled him to assign dimensions based on mass, length and time to the magnetic field. In the 1860s, James Clerk Maxwell, William Thomson and others working under the auspices of the British Association for the Advancement of Science, built on Gauss' work and formalized the concept of a coherent system of units with base units and derived units. The principle of coherence was successfully used to define a number of units of measure based on the centimeter-gram-second system of units, including the erg for energy, the dyne for force, the Berry for pressure, the poise for dynamic viscosity and the Stokes for kinematic viscosity. Meter convention, a French-inspired initiative for international cooperation in metrology, led to the signing in 1875 of the meter convention. Initially, the convention only covered standards for the meter and the kilogram, a set of 30 prototypes of the meter and 40 prototypes of the kilogram, in each case made of a 90% platinum 10% iridium alloy, were manufactured by the British firm Johnson, Matthey & Co. and accepted by the CGPM in 1889. One of each was selected at random to become the International Prototype Meter and International Prototype Kilogram that replaced the Meter des Archives and Kilogram des Archives respectively. Each member state was entitled to one of each of the remaining prototypes to serve as the national prototype for that country. The treaty established 3 international organizations to oversee the keeping of international standards of measurement. General Conference on Weights and Measures, a meeting every 4 to 6 years of delegates from all member states that receives and discusses a report from the CIPM and that endorses new developments in the SI on the advice of the CIPM. International Committee for Weights and Measures, a committee that meets annually at the BIPM and is made up of 18 individuals of high scientific standing, nominated by the CGPM to advise the CGPM on administrative and technical matters. International Bureau of Weights and Measures, an international metrology center at Chevreuse in France that has custody of the international prototype, kilogram, provides metrology services for the CGPM and CIPM, houses the secretariat for these organizations and hosts their formal meetings. Initially, its prime metrological purpose was a periodic recalibration of national prototype meters and kilograms against the international prototype. In 1921, the meter convention was extended to include all physical units, including the ampere and others defined by the Fourth International Conference of Electricians in Chicago in 1893, thereby enabling the CGPM to address inconsistencies in the way that the metric system had been used. The official language of the meter convention is French, and the definitive version of all official documents published by or on behalf of the CGPM is the French language version. Towards the SI at the close of the 19th century, 3 different systems of units of measure existed for electrical measurements. A CGS-based system for electrostatic units, also known as the Gaussian or ESU system, a CGS-based system for electromechanical units, and an MKS-based system for electrical distribution systems. Attempts to resolve the electrical units in terms of length, mass, and time using dimensional analysis was beset with difficulties. The dimensions depended on whether one used the ESU or EMU systems. This anomaly was resolved in 1900 when Giovanni Giorgi published a paper in which he advocated using a 4th base unit alongside the existing 3 base units. The 4th unit could be chosen to be electric current, voltage, or electrical resistance. In the late 19th and early 20th centuries, a number of non-coherent units of measure based on the gram, kilogram, the centimeter, meter, and the second, such as the Ferdistaka for power, the Darcy for permeability, and the use of millimeters of mercury for the measurement of both barometric and blood pressure were developed or propagated, some of which incorporated standard gravity in the definitions. At the end of the Second World War, a number of different systems of measurement were in use throughout the world. Some of these systems were metric system variations, whereas others were based on customary systems of measure. In 1948, after representations by the International Union of Pure and Applied Physics and by the French government, the 9th General Conference on Weights and Measures asked the International Committee for Weights and Measures to conduct an international study of the measurement needs of the scientific, technical, and educational communities aimed to make recommendations for a single practical system of units of measurement, suitable for adoption by all countries adhering to the meter convention. On the basis of the findings of this study, the 10th CGPM in 1954 decided that an international system should be derived from 6 base units to provide for the measurement of temperature and optical radiation in addition to mechanical and electromagnetic quantities. 6 base units were recommended: the meter, kilogram, second, ampere, degree Kelvin, and candela. In 1960, the 11th CGPM named the system the International System of Units, abbreviated SI from the French name, Le Système International d'Unités. The BIPM has also described SI as the modern metric system. The 7th base unit, the mol, was added in 1971 by the 14th CGPM. International System of Quantities. The International System of Quantities is a system based on 7 base quantities: length, mass, time, electric current, thermodynamic temperature, amount of substance, and luminous intensity. Other quantities such as area, pressure, and electrical resistance are derived from these base quantities by clear non-contradictory equations. The ISQ defines the quantities that are measured with the SI units. The ISQ is defined in the international standard ISO, IEC 80000, and was finalized in 2009 with the publication of ISO 80000-1, SI brochure and conversion factors. The CGPM publishes a brochure which defines and presents SI. Its official version is in French, in line with the meter convention. It leaves some scope for local interpretation, particularly regarding names and terms in different languages. So for example, the United States' National Institute of Standards and Technology has produced a version of the CGPM document which clarifies local interpretation for English language publications that use American English, and another document that gives general guidance for the use of SI in the United States and conversion factors between SI and customer units. The writing and maintenance of the CGPM brochure is carried out by one of the committees of the International Committee for Weights and Measures, the Consultative Committee for Units. The CIPM nominates the chairman of this committee, but the committee includes representatives of various other international bodies rather than CIPM or CGPM nominees. This committee thus provides a forum for the bodies concerned to provide input to the CIPM in respect of ongoing enhancements to SI. The definitions of the terms quantity, unit, dimension, etc. that are used in the SI brochure are those given in the International Vocabulary of Metrology, a publication produced by the Joint Committee for Guides in Metrology, a working group consisting of 8 international standards organizations under the chairmanship of the director of the BIPM. The quantities and equations that define the SI units are now referred to as the International System of Quantities, and are set out in the International Standard ISO, IEC 80000 quantities and units.